Welcome to this explainer. Today, we're unlocking the microscopic rules of organic chemistry, and we're zeroing in on the stability behind carbon intermediates. These fleeting structures are literally the invisible building blocks of everything around us, from the medicine in your cabinet to the materials in your smartphone. So if you love discovering how the microscopic world holds itself together, you are definitely in the right place. We're going to unpack a structural mystery that absolutely rocked the scientific community.
Okay, let's dive into this. When we think of chemistry, we usually picture atoms neatly locked together in stable molecules, right? But what actually happens in that split second during a chemical reaction when a molecule is transitioning from one state to another? Like, what keeps it from just completely falling apart? Well, it turns out molecular stability is this hidden, high-stakes battle of invisible forces. It's an arena where molecules deploy incredibly clever tricks to share the massive burden of electrical charge.
To solve this mystery, here is our roadmap for today. Number 1, we'll meet the carbon intermediates. 2, we'll compare classical versus non-classical ions. 3, we'll look at some clues in the chemical rates. 4, we'll unpack the great carbocation debate. And finally, number 5, we'll reveal the modern chemistry consensus.
All right, let's kick things off with Section 1, Meet the Carbon Intermediates, the prerequisites.
So basic carbocations are essentially molecules with a carbon atom that has lost an electron, which leaves it with a full positive charge. Now, in the atomic world, carrying a full positive charge is a massive, highly destabilizing burden. It's a heavy weight to carry. The molecule becomes desperate for electrons. So, for a reaction to actually proceed smoothly, the molecule has to figure out a way to stabilize that positive charge, even if it's just for a fraction of a millisecond.
Which brings us to Section 2. Classical versus non-classical ions, a tale of two structures.
In the standard textbook view, we have classical carbocations. In these structures, the positive charge is either localized on one single carbon atom or it's delocalized using familiar, totally expected methods, like resonance with an unshared pair of electrons or maybe an adjacent double or triple bond. Specifically, they do this in what chemists call the allylic position, meaning right next door to that double bond. Basically, it plays by the established rules. But non-classical carbocations, they are the rule breakers. They share the burden of that positive charge by delocalizing it in entirely unexpected ways.
Now, what's really interesting here is how incredibly strict the boundary between these two is. In a non-classical carbocation, the positive charge is delocalized by a double or triple bond that is completely outside of that normal allylic position. Or, and this is where it gets really bizarre, the charge is stabilized by a single bond. Yeah, literally a standard sigma single bond pitching in to help stabilize a positive charge. It's completely wild.
And the most famous example of this, pretty much the absolute star of our explainer today, is the Norber-Neal carbocation. In this non-classical ion, the electrons from a neighboring carbon-carbon single bond actually lean over to share the positive charge. This creates what's known as a bridged carbocation. It involves the delocalization of electrons to form a 3-center 2-electron bond. Just imagine 2 electrons holding 3 atoms together all at once, basically bridging a gap to keep the entire structure from collapsing. But how do we know this weird bridged structure actually exists? Well, let's look at Section 3, Clues in the Chemical Rates, the Anomaly.
10 to the 11th power. That is 100 billion. When chemists ran the experiments, they didn't just find a slight difference in how fast certain molecules reacted. No, they found a reaction that happened 100 billion times faster than it was technically supposed to. To put that into perspective, that's like a road trip that usually takes an entire year, suddenly taking 3 milliseconds. In science, a number like this isn't just a tiny clue. It's a blaring siren telling you your fundamental model is missing something absolutely huge.
So let's look at the hard data. When we perform acidolysis, which is a chemical breakdown using acetic acid, on 2 different structures, let's call them A and B, structure A reacts 100 billion times faster than B. Plus, it proceeds with full retention of its configuration. Why? Well, because in structure A, that neighboring carbon-carbon double bond isn't just sitting around doing nothing. It acts as a neighboring group, actively assisting in pushing out the leaving group. This staggering rate data strongly points to the existence of a non-classical intermediate. Let's call it intermediate C. The double bond actively interacts with the charged carbon, basically proving that intermediate C has to exist to facilitate such incredible speed.
And, the plot thickens with the work of chemists Weinstein and Trifon. They were looking at a carbon-carbon single bond acting as a neighboring group. They studied 2 incredibly similar starting molecules, XO2-norbornyl brozylate and endo-2-norbornyl brozylate. Just looking at them, you'd think, sure, they'll react at similar speeds. But the exoisomer was found to solvolyze, or dissolve and react, 350 times faster than the endoisomer. Not only that, but the pure exobrasylate gave a completely racemic exoacetate product, meaning an exact 50-50 mix of mirror image molecules.
Winstein and Trifan interpreted this data beautifully. They argue that in the exoisomer, the carbon-carbon single bond connecting positions 1 and 6 is in the perfect geometric position to provide what is called enantiomeric assistance. It literally reaches over from the backside to help push the leaving group off, forming our bridged non-classical intermediate. The endoisomer, however, it's totally out of luck. Its geometry entirely prevents the 1,6 bond from providing that backside assistance, which explains why it just reacts at a normal, slow rate.
And this brilliantly illustrates exactly why the product looks the way it does. Because the non-classical intermediate forms a symmetrical bridge, the 1 and 2 carbon positions become perfectly equivalent. So a nucleophile, the incoming molecule, can attack position 1 or position 2 with completely equal facility, but it can only approach from the exo direction. This perfectly explains that 50-50 racemic mix of the exo products we just talked about. It really is just an elegant, complete explanation.
But, as we know, in science, elegant explanations aren't always accepted right away. Welcome to Section 4, the Great Carbocation Debate, H.C. Brown's Challenge.
Enter H.C. Brown, an absolute titan of chemistry. He looked at Winstein and Trifan's non-classical 3-center 2-electron bond and entirely rejected it. He firmly challenged and disapproved of the very concept of sigma bond participation. To Brown, breaking the established rules of classical bonds was completely unnecessary, and he set out to prove that this whole phenomenon could be explained without inventing brand new types of chemical bonds.
So instead of a bridged non-classical ion, Brown proposed what he called the rapidly equilibrating classical ion. Think of it kind of like a windshield wiper on a car going incredibly fast. He argued that you don't have one weird bridged molecule. Instead, you have a normal classical carbocation where the bond rapidly shifts back and forth, a 1-2 shift, between two distinct structures. And it happens so incredibly fast that to our instruments, it just looks like a single symmetrical ion. In Brown's model, the molecule rapidly shifts from one structure to the other and back again in a constant rapid equilibrium. Brown suggested that this rapid migration, not some new bridged bond, is what leads to the preferential approach of the nucleophile from the exo direction, completely bypassing the need for Winstein's non-classical bridged bond. It was a fierce, high-stakes battle of ideas. On one side, you had Winstein's new bridge structural paradigm. On the other, Brown's clever application of classical, rapidly shifting physics. This debate raged for decades, driving massive amounts of experimental work. Which brings us to our final section, Section 5, the chemistry consensus, the verdict.
After an exhaustive, vast amount of research, we're talking advanced spectroscopy, supercooling, crystallography, the whole shebang, the chemical community finally reached a conclusion. The evidence just became overwhelming. Almost all chemists today accept Winstein's interpretation. The bridged, non-classical carbocation is real. That 3-center 2-electron bond exists, and enantiomeric assistance by a single bond is an undeniable reality of organic chemistry. Brown's challenge forced the community to rigorously prove it for sure, but ultimately the non-classical rule breakers won the day.
So, we've seen how molecules can bend, bridge, and completely defy our standard expectations just to maintain their stability during chemical reactions, which leaves us with this final thought. If established molecular rules can be completely rewritten by investigating a simple 100 billion-fold speed anomaly, what other invisible realities are waiting to challenge our textbooks? It's definitely something to think about. Keep questioning the obvious, and thanks for joining me for this explainer.